So today in class we didn't get a chance to finish this problem. So let me just remind you what we have. We've got a sequence. We've got a1 is the number 2. And then to get the next term, we just plug in the previous term and we square it, we add 2, and we divide by 2 times that previous term. Okay? And in class we talked about how since there are no minus signs or negatives anywhere in this, since we're starting with a positive number, we'll always stay positive. So we know that all of these numbers in this sequence are going to be greater than 0. And our claim is that it's decreasing. So we did some experiments, we saw some values. And what I wanted to do, and this is something we didn't do in class, is to sort of work through what the decreasing property would mean. So let's say that an is greater than or equal to an plus 1. Well, in our particular case, we have a formula for an plus 1, so we can rewrite that over here. And if we do some algebra, and you should maybe pause the video now and sort of work through these steps, if we clear denominators and basically get down to the end, we can determine that that this will happen if and only if, because all of these steps are reversible, if and only if an is greater than or equal to the square root of 2. Right? So let's emphasize that punchline, that an being greater than an plus 1 for this particular example is equivalent to just saying that the nth term is at least the square root of 2. Right? So how are we going to do that? Well, what we could do is I guess we could look at a graph, right? Maybe let's do that. Let's go to, I don't know, Wolfram Alpha. We'll see if this works. Let's just graph y equals, let's do x squared plus 2, and let's divide that by 2x. Let's just see what happens when we do that. Oops, I meant to divide. I did that thing where I didn't put the parentheses. Okay, so let's divide by 2x. There's my function. And oh, this is really cool. So I've got this plot here, and it looks like I've got some sort of minimum value here, right? So up here you can see that the x values are only going between 1 and minus 1. This is a more representative picture where we have bigger x range. And it looks like when x is positive, it gets really big, and then there's like a minimum here. And then there's something else going on with the negative. So that's maybe our research. Let's go back and see what's going on. So my claim, based on this graph, is that if we take a positive number x, and we plug in x squared plus 2 over 2x, then it's always going to be at least equal to the square root of 2. In fact, I'm curious if Wolfram Alpha, if we try to minimize this, it's not going to actually find it for us. But in any case, it is true that minimum value is going to be square root of 2, which is exactly what we wanted. And once we know this, we'll basically be done. We'll basically be done because we started with a number bigger than root 2. And every other term of the sequence is going to be gotten by just plugging in some previous term in for x, so like x squared plus 2 over 2x. And since this claim says no matter what positive number we plug in, we're going to get something bigger than the square root of 2. Right? And you may have noticed that there was a typo on my original handwriting, and I had to put in this condition that x is greater than or equal to 0 for this to be true. In fact, I probably should have said x is strictly greater than 0 because we can't really divide by 0. So there's even a typo still. In fact, let me just change that. Right? So that's what we want to show. We want to show if we plug in a positive number, then this fraction will be at least the square root of 2. And how do we prove that? Well, the way that we can prove that is just, for instance, we could back solve it. Here's sort of the forward direction. I can notice that if I take x, oops, I don't know how to undo that. We can do x minus 2, and if we square all that, that'll be greater than or equal to 0. If we multiply that out, and we solve for x squared plus 2 over 2x, we'll see that it's greater than or equal to square root of 2. Okay? And you will notice here in the very last step here, we divided both sides by x. That's where we needed that x was positive so that we could ensure that that inequality sign didn't flip. Right? So this is a kind of a tricky problem. It had some few steps, to show that it was decreasing. We did some algebra to see that that was equivalent to showing that an was always at least square root of 2. And we went to Wolfram alpha. Let's see if I just typed minimize. Maybe if I type critical points of this function, it's going to show me that that the critical points are happening when x is plus or minus root 2. That's sort of showing our stability point there. But in any case, the hard part of the proof was showing that every term of the sequence is at least equal to the square root of 2. Right? And we did that we could use calculus, I guess, if we had it. In our case, we went through this proof up here. Right? So I wouldn't say this is a problem you need to worry about sort of replicating or learning the techniques. You can think of it that there were a few leaps where we had a cool idea in showing that a certain inequality was coming from somewhere, for instance, maybe starting from this. What's most important is that you understand each step of this process. And so if there are any particular steps that don't make sense to you, please let me know. Send me an email. You could try making a comment on the video. I think I'll get emails about that, and then I can reply, and then other people can see that answer as well. So thanks for watching.